things today. But any questions about anything? Does homework all right? What particularly stands out is we build up some more formulas, and so over time there'll be more things to do. But we also keep looking at, how do these work? How do they work over repeated samples? So the performance of the intervals. And one topic we'll talk about today is the issue of pivot functions. Kind of more, a little bit of kind of a little bit of foundations of where some of this comes from, right? A little bit more. So we're talking about confidence intervals for a parameter. And section 7.2 we won't cover in great detail, but it makes the point that sometimes there's certain types of functions that we can apply called pivots that give us a way to make a confidence interval. So it's a little glimpse into, there's kind of some underlying theory that kind of gives a general approaches to finding confidence intervals. And it's essentially what we've used for some things. So in chapter 7.2, a pivot is a function of the data that has a probability distribution that does not involve the parameter. It has a probability distribution that's not involving the parameter you're interested in. So for instance, in our normal samples, when we take x bar minus mu and divide it by sigma over the square root of n, this thing had a distribution that was a standard normal. Normal with mean 0, variance 1. So mu is not in this. It's not here. The probability density function for this normal doesn't involve mu. So you can make a probability statement about the normal, then this thing was the thing that had that distribution, and we can kind of unpack it to get our confidence interval. But it has sigma. Sigma, when it's unknown, is sometimes called a nuisance parameter. So it's part of the probability of our data, but we don't actually know it. And it's here in one of these pivots. And if we knew it, it would be great. But usually we don't. So it sometimes causes, a little bit of let me separate this just a bit. So sigma unknown, right? That is a little something to deal with difficulty, right? So t, when we divide by x bar minus mu and divide by s over the square root of n, and the data were normal, this thing had a t distribution within minus 1. And again, mu is not here. So again, this t ends up being a pivot. So we can make a probability statement about t, and then plug in this function here, and then unpack it and come up with a confidence interval. Right? And so pivots in both of these cases were kind of key to us being able to figure out confidence intervals. And in the kind of a couple cases that the book describes, some distributions kind of get grouped together. So a bunch of distributions that depend on a location change or an average change is called a location family. So if it's the general same probability function, except you're able to move this one parameter in it. So like a normal, if you just didn't know the mean but has some fixed variance, then the mean would be all that would be changing. So there's a way to find pivots for location families. We're not going to go into the details of doing that in the general case, but it's there. And then there's scale families. Right? So if you had a normal with a mean of 0 and some unknown variance, well then the everything is centered at 0, but then how wide it is a scale change. And so there's some interesting, probability theory about general distributions that give you pivots, that give the confidence interval. So we consider just a few specific cases that are very common and you'll see all the time when you're doing statistical inference. But there's kind of a deeper theory that if you do graduate school in statistics and have to take a probability or theory class, would go into that. So they fit in with that, right? So let's consider one case. How about inference for a variance or a standard deviation? So in this case, x1, x2, up to xn are going to be IID. They're independent and identically distributed. Let's pretend that they're normal with mean mu and variance sigma squared. Right? And mu is unknown, sigma squared is unknown. It turns out that n minus 1 times the sample standard deviation over sigma squared is distributed as a random variable called a chi-square. And this chi-squares, like t, depend on how many sample points you have. This chi-square random variable is a positive random variable. Let's call this statistic here just c, kind of beginning of chi-square is a kind of a c if you write out chi, chi. Right? And so this is the distribution of x. This density is the probability density function for a chi-square with n minus 1. Right? So this thing doesn't depend on sigma squared. Right? So the probability density function will depend on the sample size n or n minus 1, but it won't have sigma squared in it. Right? And so it's a pivot. And so we should be able to make a probability, get a confidence interval for sigma squared based on that. Right? So how do you do it? Right? What's some of the process we used for the other ones? Right?
So like depending on your confidence, you find the area contained and multiply that by.
Yeah, so we can find the area and then do something with that, right? So we have this curve, this probability density. The little example that we're going to look at, just for numerical calculation, we're going to have a sample size of 25. And so if I generate 10,000 random values from a chi-square, there's our random chi-square function. It has its degrees of freedom there, and here's a histogram of those 10,000 values. Right? So I could take, I can find the lower cutoffs and the upper cutoffs for any chi-square. So the quantiles for a chi-square, the lower 0 to 5, when I have the 24 degrees of freedom, is 12.4. Let's do a vertical line at that and make it red. All right, so there's that line. The 975 point is up there. Its value, 975, is 39.36. So that's just true for any chi-square with 24 degrees of freedom. Those are the cutoffs, right? And that's kind of what's illustrated there. So when we go to, we can write that the probability that this statistic C is between these two cutoff points. What is that? That's the chi-square value n minus 1 degrees of freedom, and the other, let's call the upper one, 0.975, and then the chi-square degrees of freedom, the 0.025, is that lower area. That probability is 95%. So where those 2 points are, like my red ones on the, kind of find the center 95%, 2.5% on this tail, 2.5% on that tail. And that's a true probability statement. Right? There's no really arguing about that. That's the area under the curve and the 95%, 2.5%. It's not symmetric because it's skewed, but that's okay. So what would be the next step in finding a confidence interval? called C, right? We're going
Oh,
to
you need to solve in terms of your
parameter.
parameter
Yeah,
values.
right. So let's fix this. Right, that's the thing there. This sigma squared, right? So this thing can be put right in there, and that's a true probability statement. And then if I solve to isolate sigma squared, I'll get an interval. Right? Something on the lower side, something on the upper side, sigma squared in the middle. That's inverting the pivot like we did before. Right? So the way that this one works out, when you do it, you have the chi-squared, the lower 0.025, and I'll just leave off the degrees of freedom to save a little bit of writing. This is n minus 1 s squared over sigma squared, and this thing is a chi-squared 0.975 for the upper one. This is a little square, right? And so I'm going to, you have to kind of take this side first and solve for sigma squared, and this side and solve for sigma squared. So when you have sigma squared in the middle, you have this n minus 1 s squared over here. And the one you're going to be dividing by on this side is the smaller point, 0.025. And this one works out to be the larger one, right? Ends up being over here, right? And so that probability, when you adjust things, is 95%. Right? So we can take our n minus 1 times the sample variance and divide it by that chi-square cutoff down here, and this one up here when we get our interval. Right? So it's working with the pivot. It looks a little bit different. This is the scale family, so instead of a location family, right? So it ends up being a little bit different, but we get a confidence interval. Right? And so if you look up in an introductory textbook a confidence interval for variance, this is usually what it does. We won't do, there's a few other pivots that are common, but not a whole lot more, but that's the general idea. So let's say we have an example, right? So I took an example from a book by Sokol and Rolfe, classic book called Biometry. The third edition of this, about page 50 in that book. There are statistical analysis of the femur length of a certain type of aphids. And the aphids, there are mothers, some of them are called stem mothers, that generate offspring. And it's a species, Pemphigus popule with trans versus. Right? So I bet we could look up a graph of that. But for these 25 aphids, they measure the length of the femur on these is the standard deviation of these 25 measurements, 0.3464. This is millimeters, tenth of millimeters. So these things are pretty small, and it's making pretty precise measurements of these little tiny measurements there, right? And say we want a 95% confidence interval for the standard deviation of femur lengths in this population, right? So some people like E.O. Wilson study ants, other people study aphids, and so biologists study all different types of insects. And take very precise measurements on these little tiny things. Right? Microbiologists would have, their organisms they study, their sizes and different characteristics, the length of the tails on different flagella and things like that. So, what's the confidence interval? Well, with n equals our form, this is sigma. We can do first a 95% confidence interval for sigma squared. That's the formula we worked out. So we'd have 25 minus 1 times the 0.3464 squared divided by a chi-square value, and 25 was minus, this was 39 something, and 25 minus 1 times the 0.3464 squared. Up here, this one was 12.4 for the cutoff values from R. So in R, here's our cutoff value, 39.4, 12.4. And so we get an interval for sigma squared, that's 0.0732 up to 0.2322. We can check, one quick check is if we square this thing, s squared, if you square that, right, it should be kind of near these other values, the s squared. I did compute that, where is that? Oh, there it is, 0.11999, so about 0.12. So the square of this value is kind of in the middle of those, which is good. It's not exactly in the middle, it's not symmetric, because the chi-square is not symmetric. So to then do a 95% confidence interval for sigma, you can just take the square root of both of these two sides. Right? Those are all positive values, so if it's in that probability on the square scale, and then taking the square root scale, it should be, actually it expands back up because we're less than 1. So you take the square root of both those values, you get 0.270 up to 0.482. Right? And this was, the units of measurement on this is in tenth of millimeters. So if you're interested in that species, the variability of the measurements, right, you can get a 95% confidence with that. It's based on a pivot. So we get that confidence interval. But any questions about? Yeah.
So all parameters fall into either a scale family or location family?
No, there's location scale as well, and then there's some things that have exponents put on them. Right? You raise something to a power, and it's maybe not nonlinear, so some things would be outside of that. But some things, like normal and a number of these other things, a lot of these things like exponentials and gammas and chi-squares are all positive. So if you multiply the random variable by something and change its scale, it's still a gamma or a chi-square. It's still that same type of distribution, but just with a different parameter value. Some other things, yeah, some don't quite fit into that, but the ones that have discrete support, like on certain integers, you multiply them by something or shift them, and they're not quite the same. You might call them a shifted value. Kind of expand the notion of the family. You can kind of make it work out, but it's not quite as common. So that's kind of there's general ways to get some of these. What we want to introduce now is a confidence interval for a proportion. Okay. So this will follow a lot of the logic of the other work, and it is also a very common case, right? So in this case, we're going to say that if x is what we measure, it has a binomial distribution with n trials and probability p. So in this notation, n is the number of trials, number of independent trials. And our parameter is p, is the probability of something happening, so a success on one trial. Right? So success is, kind of generic, just kind of probability of something, right? Something that you're trying to count. And each trial is either going to be success or failure. And you do n times, and then x counts the number of successes. Right? So it gives a certain probability model, right? So if people say there's a random sample and they're counting the number of people that have some characteristic or answer a certain way, the random sample is kind of implying that they're independent. If it's just from a population and they're not breaking it out by different pieces, you could have a constant value of p in that group, and so on, so it generally would apply. The other way that we've considered this, when we're doing with the likelihood and everything, is that each xi was either 0 or 1 and had a probability of p over 1 minus p. And the x that we're considering here, you could think of as just the sum of those. Right, so adding up the number of successes and counting them. Now, from probability theory, the expected value of the number of successes is just n times p, and the variance is n times p times 1 minus p. And if we let our sample proportion p hat be x over n, if we divide that by n, the expectation gets divided by n, but the variance gets divided by n squared. And so we end up with the relationships of the expected value of p hat is just p, and the variance of p hat is p times 1 minus p over n. Or if you take the square root of that, the standard deviation of p hat is our p times 1 minus p over n. The square root of all that. And so those are just a few things from probability theory. The other thing that you get, right, is central limit theorem. Because p hat's like an average. Right? You're adding up all these 0, 1 values, right? And then taking the average, so this is an average. It's an average of 0, 1, different values. So the central limit theorem would say that p hat distribution is approximately normal, as long as you have large enough sample size. So central limit theorem says that p hat is approximately normally distributed. It's going to be centered at p, and its variance is p times 1 minus p over n, whatever p really is. And so this works if our sample size is n times p is greater than 10, and n times 1 minus p is greater than 10. Right? So if you have an if you're likely to have a fair, a decent number of successes and a decent number of failures, then that sampling distribution is roughly normal. If for p around 0.5, this would say 20. You need a sample size of about 20 if it's at 0.5. If p is more something like a quarter or 0.75, you would need more like 40 for that to happen. So as the p actually gets closer and closer to the edge of the space and everything clumps at 0 and 1, and so the totals are all clumped at one side, you need more for it to start looking normal. But anyway, right, this looks like a normal. So we're going to have something like a pivot, right? If we take p hat minus p over the square root of that, we get a normal, a standard normal. So p hat minus p, and then p times 1 minus p over n square root, that thing should be approximately like a standard normal. And so kind of following that logic, we can take p hat plus or minus a certain number of standard errors, and that would be a confidence interval analogous to the other ones that we have, right? So there's a p hat plus or minus 1.96. So if we want to do 95% confidence interval for p, we have this 1.96 as a cutoff. And for z and t, we only have one number. I mean, there really is a positive number and a negative number. There is an upper and a lower. It's just symmetric. So it's 1.96 and negative 1.96, or 2.02 and negative 2.02 for some t distribution. With the chi-square, they weren't symmetric, so that's why we had two different values we had to keep track We really have two values here, but symmetry means that it's plus or minus that. And then we have the p times 1 minus p over n square root, right? Is that a 95% confidence interval? Can you actually compute that and tell me what the lower and upper value are, right?
You don't know what P is.
Yeah, we don't know what p is, right? So there's this little, p is kind of a nuisance for itself. You get the variance, the mean and the variance are, the variance is a function of the mean. It doesn't happen for normal. Normal's not the only one. But so that's a little wrinkle, right? So standard introductory textbooks say plug in, p hat, and so we report p hat plus or minus 1.96 p hat 1 minus p hat over n, right, for that. And that should work pretty well, right? Large enough sample size, the values of p not too close to 0, not too close to 1, right? And then you'll get something pretty close. That should cover about 95% of the time. The book does a little more advanced presentation, right? So if you put this thing, right, so what does the book do? So this is kind of a standard formula that you can calculate, and it should be pretty accurate, right? But people have considered this for a while, that if z is our p hat minus p, p1 minus 1 minus p over n square root, right? Using this idea of a pivot, right, we would say, our negative 1.96 is less than or equal to that z value, and that's about 95%, right? And then go from this to find a statement where p is in the middle, right? Well, p's up here. Oops. P's up here and it's down here. So a solution to that problem is a little more involved. It's actually a quadratic equation, and somebody named Wilson published a solution in 1927. So it's been around for a while. But that's the interval that's reported in R, our proportion. Right? And we're not going to write down the whole formula because it's kind of right. And so the proportion.test is the command. It's about test of a proportion. It also gives a confidence interval for proportion. The article that it's referring to, this Wilson one down here, is this one, 1927, Journal of American Statistical Association. Right. You can click on it, and it will, Taylor and Francis publishes with the American Statistical Association. And so there's a kind of the beginning of the, Edward Wilson was at Harvard School of Public Health at the time, and it has a note. And I don't see the whole thing there, but I can get the citation, Journal of American Statistical Association, volume 22, issue 158. So if I go to just JASA is the brief name for Journal of American Statistical Association, and JSTOR, which stores things, I can go there, JSTOR, and it has the articles going back in time. So it has the articles back in the 1920s. This one was in the first one. It was in this one based on the page number. And looking through there, I kind of looked through this. A lot of these articles for the American Statistical Association, this issue anyway, back then were finance related. Or 1927, a couple of years before the Great Depression, stock market going crazy. Looks like a lot of statisticians are, maybe this is a special issue because it's so focused on that. But here's the probable inference, law of succession, and statistical inference. So you can get the PDF there. Oh, why did I do that? PDF, accept. That's weird, it doesn't like that. But anyway, that's the article. And so they kind of talk about the first way, of doing it. Notation's a little bit different. But essentially this rule of Chebyshev's inequality that gives you the plus or minus so many standard deviations in there, but then presents it as an improvement. Right? And that's kind of the equations that are done there. And then it's a little more discussion and not much numerical example, and kind of says how it's similar to things. There, but anyway, that's the formula that then was seized on, and that's what it's computing. So if you're interested in history, statistics or things, that would be something there. So let's imagine an example, right? That according to the Gallup poll, right? Gallup doesn't do so much of a poll anymore, but they mostly do commercial newsletters of things. But they do publish a few things from polling. So from their recent surveys, they've done presidential approval ratings going back for decades to the Second World War. And according to this, the approval for Trump is at 39%. Right? Approval. Disapproval for President Trump's job in office is at 57%. And so then no response or do not know, that adds up to 80, 96, must be about 4%. Right? There's a category there. Right? I don't see without paying for their newsletter what the sample size is. But usually for these things, the sample size, did I put any numbers in here? There, I put my numbers. If the numbers are about, let's say about 400 people for a survey, it might be 1,000 or so, but let's say it's 400, right? What's a 95% confidence interval for these different things, right? So our formula, right, would say 0.39 plus or minus normal value of about 1.96, and then our variance estimate. So just using the simple formula, 0.39, 1 minus that over our 400, right, is going to give us an interval that's like 0.521 up to 0.6185 or so. Right? And no, that's the wrong one. Let me not put those numbers in. That's the next one. So let's do it on the computer. Trying to just see what the number would be. So if we do that so-called manually, right, 0.39 minus 1.96 times the square root of 0.39 times 1 minus 0.39 over 399 over, say it's 400, we get that as a lower interval, right? And that one is an upper interval. So we'd be 95% confident that the approval would be somewhere between 0.34 and 0.44, right? So we'd be pretty sure it's below 0, unless there was a massive campaign for people who support Trump to not participate in Gallup polls, right? Missing this could cause a bias. Or if people not answering their phone, if there's a huge difference there, maybe it would be shifted somewhat, but that's pretty convincingly that it's there. What does the proportion test do? Now the proportion test, well, it gives you a little prompt here in this RStudio, that it needs X, it needs the number of yeses and the sample size. So before we do that, 0.39 times 400 is about 156. It works out evenly, that's nice. Prompt out test. If you have to take published results, they don't always come out exactly to integers. Maybe you have to guess and round a little bit. So if we had 156 yes out of 400 trials, it will give this one sample proportion. It gives it with a continuity correction and uses the Wilson method. And so it comes out 0.342 up to 0.44398. So it's different, kind of in the third decimal place, maybe really in the fourth decimal place. So it's slightly different, but pretty much the same. And again, thinking about which of these works better, the standard case or this one? Well, this one that uses a little more information and a little more exact and doesn't just do a plug-in a little bit earlier, probably is going to be a little bit better, right? But if you have 95% coverage, this one probably comes up a little bit better in terms of percentage, a little bit better in terms of width, right? This one is not necessarily symmetric because the sampling distribution is not exactly symmetric, right? Because if it's away from 0.5, it's tilted a little bit, right? It's a little bit skewed. Right? So this one will be a little bit better in terms of percent coverage and maybe width than that, but you're comparing kind of 94% versus 95% or 93% versus 95%. But in the long run, if everybody's going to do an interval and they can do this one, it'll be just that little bit better in terms of things. What would happen if we had a bigger sample size?
And the same number of yeses?
Well, no, probably the same proportion of guesses, right?
It would be narrower.
Yeah. So if we had the same proportion, but this was based on 4,000, or you're going to have 4,000 down here, you're going to be narrower, right? So for instance, in this case, if we did our interval, go up here, plus, make this kind of plus or minus 1. If we had 4,000 in that, our intervals become narrower, right? They don't go down by 1/10, right? This just goes, it's about half the width, right? Our proportion test, if we had 10 times as many yeses out of 10 times as many trials, we're going to get an interval that's kind of the same. The accuracy doesn't go down real fast because of the square roots, right? So if you multiply the sample size by 4, the interval becomes half as much, right? Because of that factor. And you can plan a little bit, right? You can use this margin of error, at least in the simple formula, right? The margin of error for the simple formula was 1.96 p times 1 minus p over n and the square root of that. Right? So if you want to know a proportion with a certain accuracy, plus or minus 3%, plus or minus 5%, right? You could use this to come up with the sample size that we would need. So I'm just going to call this m to write less. So if we square both sides, 1.96 squared, p times 1 minus p over n. And so if you multiply both sides by n, you'll get n over here, and it'll cancel this one. If you divide by m squared, 1.96 squared, p times 1 minus p over m squared, right? Gives you an equation for a sample size. For planning purposes. Right, so you can choose something like a margin of error, so the margin of error is something like 0.05, or a margin of error or something like 0.03. And in your statement, you're 95% confidence it will be your estimate plus or minus 0.03. And it's going to incorporate the 1.96 in there. And the question then, what is P? Right, P is still involved there. So sometimes you might do a preliminary study, have some idea from the past, like this Gallup survey done every 2 weeks. It's not going to change much from 39%, 40%, maybe go 45, go down a little bit, so it's doing it repeatedly over time, they'd have a sense of where the proportion is, so they can plan for the next one. Right? Another way that people do planning is be conservative, right? What's the maximum that you would need, right? What is maximum necessary in to get a certain margin of error? 1.96 is chosen, margin of error is chosen, so it just depends on p. So what value of p gives you the maximum of the p times 1 minus p? Right, so p is between 0 and 1. So if you graph this thing,
Oh, it's 50%.
50%, yeah, it comes up here and then goes down, right? So here's 1/2. The p times 1 minus p at the maximum turns out to be 1/4. You can use calculus to find that. So p times 1 minus p is p minus p squared. And if you differentiate p minus p squared with respect to p, you get 1 minus 2p. If you set that equal to 0, then p is 1/2. Right? And so the maximum of this variance occurs at p equals 1/2. Right? What happens at p equals 1/2? Half the time you get a success, half the time you get failure. So you get the most variability in your outcomes. Right? And as you add up the zeros and ones, you get the biggest range. If p is very near 0, you get almost all zeros, and it's all clumped down there. So if you put that in, you can get a sample size. When it's 0.05, you get something like 384 as a sample size. To get to 3% plus or minus, you have to go up to more like 1,000 or so. And just working that out, if p is 1/2. If you're sure that p is going to be smaller, like 1/4, you can put that in there and advocate using a slightly smaller sample size. The reality in surveys, though, is often there's often a lot of different things people want to know. So there's going to be approval on, Trump. It's going to be concern about the environment. It's going to be, would it be acceptable to raise taxes to pay for health care? There'll be all these different things. Some of them are going to be near 0.5, and some are going to be away. So often 0.5 is used as kind of a compromise. And the reality of surveys is, in studies, is you often look overall, then you look by subgroups, you look Democrat, Republican, Independent. So you often figure out sample size for a bunch of different scenarios and probably take a little bit more if you can and anticipate a non-response rate. So to get, 1,000, if you think that you're going to get a 30% response rate, you might try to call 4,000 people, right? And if you want to get males and females or Democrats and Republicans with kind of an equal split, you might call 8,000 people. So it's this N is useful, right? It's realistic, but that's what you would do with an experiment. If you're experimenting with beakers and things that you control with a low failure rate and things like that, it has more direct. But calling people on the telephone and things is not easy anymore, right? But any questions about? So this is related to pivots or the probability, and the easier version is pretty close to a pivot with just a plug-in put in there. And the ones that are published and done with least proportions don't make that much of a difference in terms of the formulas, but gives a slight difference in the formula. The other thing that we can do with this is a difference of proportions. So if you have two independent samples, so you had N1 from the first group and N2 for the second group. P1 is the proportion for the first group, P2 is the proportion for the second group. And we want to compare them. Are the rates the same in the two groups? We can be interested in the parameter that what is the difference? And if they're both binomial, and both independent samples, both binomial experiment type of scenarios, our estimator can be just the sample proportion in one minus the sample proportion in the other one. Probability theory. As long as both samples are adequate size, the normal approximation works pretty well in both. Right? This is approximately normally distributed, centered at the parameter we want, and then the variances add. Right? Standard deviation. The standard deviation I'll write down here for more space. You get the variance of the first one, P1 times 1 minus P over N1, plus the variance of the second one. Because the samples are independent, and variances square everything, the difference of the two estimators, the variances add P2, 1 minus P2 over N2, and the standard deviation is the square root of that whole thing. Right? So based on what we've seen, what's one way to do a confidence interval for this? What would the formula look like?
1.96 plus or minus P1 hat times P.
Something like that, yeah. So we centered at the estimate, right? P at 1 minus P2 hat, right? Plus or minus 1.96 times what?
You plug in the
Plug in P1 hat, P2 hat here.
and one.
Standard error, right? So a bunch of these, particularly for the location family, have kind of the estimate theta hat plus or minus a distribution value times the standard error, right? And so in this case, P1 hat minus P2 hat plus or minus, we were going to use a normal value, and then standard error, and maybe some estimate of the standard error, the little hat on that one too, right? Standard error of theta hat. And so P1, 1 minus P1 over N1, P2, 1 minus P2 over N2, the square root of all that, and because we don't know it, we're going to put in, right, these estimated proportions there. So it kind of looks like our other location family, pivot-based confidence intervals, and again, it should work pretty well. So imagine, I didn't see, so approval for President Trump. Let's say Democrats, say the sample has 200 of them, and Republicans, say there's 200 of them. Of course, there could be independents, or I'm not going to tell you. So that approval for this group, put a little d here, is 10%, fairly negative. But for Republicans, say it's 70%. These two would average out to the 40% as reported, so that's why I kind of made it that way. Right? So we could do a 95% confidence interval for difference in proportions, you know, for approval. Okay? All right, and let's do Republicans minus Democrats. You could do Democrats minus Republicans either way. But if I do it this way, I'm going to get positive values. And so it would be due to the amount by which Republicans have a higher rating than Trump. So you could phrase it like that. Right? So there's a difference of 0.6 plus or minus our 1.96. You're going to have 0.1, 0.9 over 200. And 0.3, 0.7 over 200. Square root of all that. Okay. And this thing comes out to be like 0.52 up to 0.68. So the difference between Republican approval versus Democrat approval is we're 95% confident it's between 52 and 68%. Pretty big difference. And that reflects some of that. These are hypothetical numbers at this point, but it could maybe represent fairly polarized, definitely polarized. Right? But anyway, that's a confidential matter. So, you know, single proportions, double proportions, means, maybe variances. That's a lot of things that you'd see reported in articles or based in the news. And eventually we'll get into some more complicated things, but that illustrates the idea of significance. But any questions? There's some mention in the book, and when they talk about these different variations in confidence and procedures, some are called score values. Well, the score function has to do with the log likelihood. So there's some connection there between the curvature of the log likelihood and how fast the derivative is changing, and the formation of some of those intervals. So the score or wall was kind of average value of that, more like information. So there's some connections there, but I don't think it's really necessary for us to go into all those details of why they're called there. But there is some kind of underlying reasons, and it's largely through the likelihood function that we did. So, okay. So homework is due. If you haven't put it in the pile, go ahead and do that, and I'll try to get the next one posted pretty quick. You too? It is getting colder.
Yeah. It's my first day wearing this jacket.
When you're ready to talk about things.
Yeah.
I know, kind of the persistent rain eventually gets you.
Here we go.
Yeah, see ya.
Have a good weekend.
Can I have the an hour later? Like,
Yes.
Like for some reason, like my data doesn't come out, so I'm trying to figure out.
Okay.
You know.
Why don't you try that? If I'm not in my office right at that time, you can put it under the door and I'll get it. So
Yeah.
go ahead and try it.
Yeah, thank you.
Okay, sure.
Do you want this too? I don't know.
That's the archive. Do you want to just keep it with it so that you have it all together?
Might as well.
At the end, we do a project where you can investigate something, maybe through simulation or apply it to a data set.
Yeah.
So having the R code could be useful for that purpose. once you
And
do
then
it.
did I not hand in homework 5?
I was looking for it.
Okay, I remember doing it.
Yeah.
I'll check through my stuff and see if I
Okay.
can find it anywhere.
Yeah, if you locate it, show me the paper.
Yeah, or I'll just do it again. I don't know. I feel like I remember doing it. Pretty sure I remember doing it.
So some of them came in under my door or in that
Yeah.
thing, and so a couple of students said they just didn't hand it in on Friday, or.
There's also just a lot going on, so I might have forgotten to.
So
hand
if
it
you
in.
find it,
Put
you
somewhere.
let me know. So.
Alright. Thank you.
How are things going this semester?
Pretty well. Busy.
Yeah, we're at the halfway point. And
Yeah. Honestly, most of my classes, like most of my stress is just coming from anatomy, but other than that, but everything else seems to be going well.
Good.
Then click away. Very good. Alright, thank you.
You're welcome. See you. Have a good weekend.
You too.